A water wheel is constructed with symmetrical curved vanes of angle of curvature theta. Assuming that friction can be taken as negligible, the efficiency eta, which is the ratio of output power to input power, is given by this formula here. Big V is the velocity of the jet of water as it strikes the vane. Little v is the velocity of the vane in the direction of the jet, and theta is constant. We want to find the ratio little v over big V, which gives maximum efficiency, and we want to find the maximum efficiency. So we want the ratio little v to big V. This will be our independent variable, and eta will depend on it. So we want to rewrite this so that we have eta as a function of little v over big V. So to do that, we can take this factor up here, big V minus little v, put it over big V squared. Big V over big V squared is 1 over big V, and then we have little v over big V squared, and we can take out 1 over v, and we're left with 1 minus little v over big V. 1 over big V is taken out, and we have little v here. We can put that on top, and then we're left with the 2 and the 1 plus cos theta. So we want our dependent variable to be little v over big V, so let's call that x. So we want to find a value of x that maximizes eta. So we want a stationary value of this function. So we want to solve the equation d eta dx equals 0. So we want a value of x that gives a stationary point for this function. Now we could use the product rule for differentiation here, but it's easier just to multiply this out. The 1 plus cos theta is just a constant. So straightforward derivative here of 2x minus 2x squared, and we're just multiplying by the constant 1 plus cos theta. So we set this equal to 0, and we solve. Well, 1 plus cos theta is a constant, we can just divide out by that. So we solve 2 minus 4x equals 0. We just get one solution. So this must be the solution that we're looking for. Now, how do we know that this value of x maximizes efficiency, maximizes eta? Well, it's fairly clear that the ratio that minimizes efficiency is 0. You see, if x is 0, we get eta equals 0. That's the minimum value the efficiency can have. So since we only get one solution, it must be the value of x that maximizes efficiency. And we can confirm that by taking the second derivative. So if we differentiate this a second time with respect to x, well, the 2 just goes out. If we differentiate this term, we get minus 4 into the constant 1 plus cos theta. Now we're assuming here that theta is some acute angle. So the cos of theta is positive. That means that all of this quantity here will be negative. And if the second derivative is negative, it means that we have a local maximum of the function eta at x equals a half. So maximum efficiency occurs when x, which after all is little v over big V, equals a half. And to find that maximum efficiency, we plug a half in for x up here. So we get 2 halves are 1, and we have 1 minus a half is a half, so we end up with a half into 1 plus cos theta.